Alright, and with sigma notation, this is the uppercase sigma. This symbol here, it's a Greek letter. And it basically means to sum things up. And so if I had the summation of, let's say, n equals 1 to 4, of, I don't know, let's say I had x plus, or n plus 2. Then this lower number here, this is like a lower boundary of summation. The number 1 is. The number on the top 4, that's an upper number of, or an upper boundary of summation. And so the way it works is you would simply plug in a 1, so you would have 1 plus 2 plus, and then you would plug in a 2, so you'd have 2 plus 2 plus, and then you'd plug in a 3, 3 plus 2 plus, and then the upper boundary was 4, so that's, we'll plug in a 4, and that's where we would stop. Alright, and then we would simply just sum all of these numbers up. So what is that, 18? Alright, so that's summation notation and basically how it works. It just means to sum things up. And so, I mean, let's say, so here's a summation that we're going to be using today on in the lesson. Let's say I could write this summation, and you'll understand it a little bit more when we use it. Let's say I had the summation I equals 1 to n of f of x sub I times delta x. Now f of x sub I, that would be a y value. Now you'd plug in some x value into a function and you get a y value. And then delta x, that would just be a change in x. Maybe that's constant, that's not going to change. It's just going to be, it's a change in x that we would use every time. And so I could expand this. Of course, it could go on forever and ever to the nth term, because that's, this n right here isn't a number, it's a variable. But I could expand this a little bit and show you it'd be like f of x sub 1, of course again that's a y value, times delta x, plus f of x sub 2 times delta x, plus f of x sub 3 times delta x, and then again it goes on and on forever. So I'm going to put this ellipsis here that signifies that it goes on and on forever, and then I'll say plus f of x sub n times delta x. Now, since I'm multiplying each one of those terms times delta x, that's going to be a number, like a change in x that's going to be constant. I could also write this as delta x times f of x sub 1 plus f of x sub 2 plus f of x sub 3, and then dot 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 plus f of x sub n. And so the reason why I'm able to, I would be able to do that again is because you're multiplying each time by some constant that's going to be a change in x, a delta x. And it would be a lot easier to work it out this second way and find values of y for each x value. See what the y is equal to. And then sum all of that up and then multiply it times delta x. It would just save you some work from having to find out what y equals, multiply it times the change in x, find out what y equals, multiply times the change in x. Anytime we can factor terms out, it's good to factor them out. Okay, and this notation looks a little crazy right now because we haven't used it, but we'll use, even if we don't write the sigma notation every time, we're going to use this notation here today, and I'm going to show you how. So today we're going to talk about area. One of the reasons that, or one of the easiest way to show you how integrals can be used, or one of the reasons that integrals came about, was because of trying to find area of regions that normally we would not be able to find the exact area of. It's easy to find the area of, say, a rectangle or a triangle or a circle because we know all the formulas. However, and you don't have to copy this graph down. I'm going to write something like this down a couple of times today. Let's say that I just had this graph right here, and I wanted to know the area from here to here under the curve. Well, that's definitely, it's not, you see it has a curved top here, so that's going to give me a problem. It's not a square, it's not a rectangle, it's not a trapezoid. It's close to being a trapezoid, but it's not a trapezoid. So back before mathematicians understood I guess summation notation and how to evaluate that, along with integration, the closest that they could get was just to estimate the actual area under the curve. Okay, and so that's what we're going to be working on today. How did mathematicians or engineers, how did they figure out that area under the curve, maybe for an archway or for some other shape, unknown shape? How did they figure that out, or how did they estimate that? You know, even a long time ago, before people had figured out how to find the area of a circle, I mean, do you know what they did to find the area of a circle? They had to get an approximation because they had no concept of pi. They knew there was probably some formula out there, but if you start, if you inscribe a, let's see, rectangles within a circle or a polygon within a circle, and if you can figure out a way to find the area of the polygon, then you can get an estimate of the area of the circle. For example, let me show you these polygons here. This is from your ebook. Again, this is just, you know, by exhaustion is what this is called. Sometimes proofs in mathematics can be done by exhaustion. But, you know, why they say by exhaustion? Because it's exhausting to have to do all the math to figure out the area. You see, there's a six-sided polygon here inside and then on the outside as well. And so if they figured out the area on the inside, and they could figure out the area on the outside by finding the area of the triangles, then they would have like an upper boundary and a lower boundary, so they would know the actual area of the circle was between those two. Look here, this is, again, by exhaustion, n equals 12. Who would want to do all of those calculations? But if you did find the area of the 12-sided polygon inside and the area of the 12-sided polygon outside, you would have a much better estimate as to the actual area of the circle. And again, if you're thinking, why didn't they just use pi r squared? It's because they didn't know what pi was. You know, pi was not found until a lot longer, you know, than say the Greek times. You know, it took a while to actually figure out the transcendental number pi. And it's a transcendental number. It's called that because it's a symbol that stands for a number, just like E is a symbol that stands for a number. And Archimedes, he did a lot of work trying to derive formulas like for ellipses and parabolic regions and all of that by exhaustion. So he was one of the first. Well, let's say that we wanted to find, let me find us a good curve here. I'll try to sketch this as good as possible. So let's say that we had f of x equals x squared plus 1, and we wanted to find the area. Let's find the area. Of course, this is going to be an approximation under the curve, and we'll graph the curve from, or actually instead of from, let's use the word on, and then I can say the interval from 0 to 2. Okay, so I'm going to give you a rough sketch of that graph. You may want to write it down. I'm probably going to sketch it a couple of times here. And I will try to mark out a couple of evenly spaced. My scale on my X is going to be different than the scale on my Y, just to get a better picture, which is okay as long as I understand that I'm using a different scale. Okay, I spaced it out just a little bit more. All right, and so we know that x squared plus 1 is a parabola, or a U-shaped graph opening upward. And from Cal 1 you can figure out a couple of things, those tools that you learn in Cal 1, like critical numbers to see where the minimum value would be. You can tell concavity by using the second derivative. You can do all that. Well, we really don't have to use all that on a graph as simple as this. We just know that it's going to be a U-shaped graph opening upward, and it's going to go up something like this. On the from 0, here's x equals 0, here's x equals 1, and here's x equals 2. So of course, if I drew the whole graph, it would go up like this on the left side. But the problem that I'm looking at is finding the area under the curve of x squared plus 1 between the values of x equals 0 and x equals 2. All right, so here's x equals 0, and here's x equals 2. And I want to find, and I'm sorry if I color outside the lines. I made, you know, one of the only C's I made in my life that I can remember was like in the 3rd grade in coloring. It's just, I'm not that great at coloring, but it's okay. The computer helps me a lot. All right, so that's what we're trying to figure out. Now, if I just wanted a, let's see, this intersection point right here actually supposed to be 5, because if I plug a 2 in right here, that should be 5. So I'm gonna cheese this a little bit and maybe not space them out as much. We'll just pretend this one's down a little bit. Okay, so they're not really spaced out that close together, but just know this is 5. Okay. So if I wanted an estimation of the actual area under that curve, then one thing that I could do, if I, and don't copy down what I'm about to write down, because I'm going to erase it a couple of times. I mean, you can, but you'll have to draw the graph over and over. So if you have different colored pens or pencils, you might be able to do that. But one way that I could estimate that, and it would of course be a rough estimate, would be just to make a rectangle, right? I could just draw a rectangle there and figure out the area of the rectangle. Okay, so what would the area of that rectangle be? Well, you gotta, it's length times width, right, or base times height. So it would just be, my x is, so here, let me show you, my y value, or my change in y, is 5, and my delta x, or my change in x, is 2. And so I would get 10 square units. Now that estimation that I just did, do you think that would be more or less than the actual area? Of course, you could see it would be more, right? Because you're missing a lot of stuff in here that's not in the shaded region. Okay? Well, what if instead of one rectangle, I said, well, how about, well, we know this is the number 1 right here, and if I was to plug that into the function, if I plug a 1 in, I should get out a 2. So what if I made a rectangle right here, and then from there I made another rectangle. Let's see, yeah, let's make another, I guess that would not be that good. Ooh, look at me, I know that I'm talking about the space under the curve. And then I made another rectangle. Let's say we went up here to where x was 2. So we have one rectangle that's going to have a height of f of 1, and we have one rectangle that's going to have a height of f of 2. And what do I mean by that? I mean, if I plug in a 1 into my function here, then I'm going to get the height of the rectangle, this first one. If I plug in a 2 right here, then I'm going to get the height of my second rectangle. Okay? Now notice that my width, even though it may not appear to be, my width is uniform. From here to here is delta x, or my change in x, is 1 unit, and from here to here my change in x is 1 unit. Okay? So this area would be equal to, so I got to get the height of this rectangle, so I'd say f of 1, I'm going to start using a little notation here, times the delta x, or the change in x, which is the width, so times 1, plus, now I would need to get the height of this rectangle here, which is f of 2, times the width of this rectangle, which is 2. Alright, so if I find f of 1, no, the width is not 2, is it? Did I just lie to you? What's the width? The width is 1. The width is constant because we divided it in half. I apologize. So f of 1, I plug a 1 in up here, I work that out, and I get 2 times 1 plus, and then if I plug a 2 in up here, I would get 4 plus 1, which is 5. and then again the width was 1. So I would have 2 times 1 is 2, plus 5 times 1 is 5, 2 plus 5 is 7. So do you think that that area would be more or less than the actual area? It would actually be more, because look at all of this extra stuff up here in this rectangle, and look at all of this extra stuff up here in this rectangle. If I'm trying to find the area under the curve, and in my drawing I have extra stuff up on the top, then of course this would have to be bigger. All right? So that's the type of rectangles I would get if I started on the right side here and made a rectangle and then made another rectangle. So these are just estimations, and you say, why would we want to estimate? Well, we want to estimate because we really don't know how to find the area otherwise. There's no tools that we have available that have taught us how to find an estimation. Now, there is a shape that I could use, and we're not going to do it today, but I'm trying to erase that one thing, and I erased everything. If I was to make a trapezoid here, and I'm not going to calculate this area, but just to show you, if I was to make a trapezoid, and find that area, then, and we have a formula for the area of a trapezoid, it's pretty easy, then I would get an area that would be slightly less, but still it'd be really close, wouldn't it? It would be really close to the actual area, which is kind of cool. And one of the optional sections that we go over is called it's finding area under the curve using a trapezoidal rule. And instead of making rectangles, we make trapezoids. All right, but we have to follow a different formula for that, because the formula of a trapezoid is a little different than the formula for the area of a rectangle. Okay, so every time we are trying to find the area under a curve, we're going to have to figure out the height of the rectangles, because we're going to use rectangles to estimate, and we're going to need to find the width. And the width is always going to be the same number, okay? So the change in x, that's going to be the width of each rectangle. And the way that you find the width is you say the furthest or the biggest number in your interval. So let's say that we were integrating from, or I'm sorry, we were estimating from A to B. So our formula would be B minus A divided by the number of rectangles that we want to put under the curve or above the curve. Because we could do better than just 2. Why stop at 2 when we could do 4? Why stop at 4 when we could do 8? Why stop at 8 when we could do 16? So, of course, the more rectangles that we have, the harder it's going to be to figure out, because we're going to have more calculations that we're going to need to do. Now, also, it's going to matter which side we start on to get our heights. So, if we start on the left side of the graph, if I start over here on the left side of the graph, and you don't have to copy this down, but I just want you to understand the concept. If I started at the left end point here at 0 and use that to get my height, so let me see if I can erase that without erasing everything. Probably not, but we'll give it a go. There, I need to draw that back in, and we'll put a rainbow colored line there. Rainbows make everything better. All right. So if I started on the left side making rectangles, and I wanted 2 rectangles, I would have to plug in f of 0 to get the height. And f of 0 would give me 1. All right, and so that would be the height of the first rectangle. And then if I started at the next number to get my second rectangle, I plug in f of 1 all right, and I would get out a 2, and that would give me 2 rectangles under the curve. That's if I started at the left end point and I wanted n to equal 2. And I'll go over this again, but I just want to show you what I'm talking about. Now, if I was to use the right end point to make my 2 rectangles, I started at f of 2. And I used f of 2 to get my height. My height would be 5. And then f of 1 to get my height of my second rectangle. F would be, or y would be 2. So you see my 2 rectangles would be above the curve if I started on the right side getting my, making my 2 rectangles. It'll be under the curve if I started on the left side. Now that's just because of the way that this graph is. Sometimes starting on the right side may put the rectangles under the curve. And sometimes starting on the right side may put the rectangles above the curve. It just depends on what curve we're looking at. Okay. So I'm going to put another drawing up here, one from a text or web page that I use a lot. And you don't have to have this exact drawing, but just try to sketch this out. It looks a lot better whenever I get a picture from the book. So this is the same graph. This is f of x equals x squared plus 1. And we're looking for the area on the interval from 0 to 2. All right, so we are going to start with the, let me make it a different color. We're going to start with the right endpoint. And so the right endpoint is 2. And we are going to let n equal 4, meaning I'm going to make 4 rectangles. The more rectangles that I make, the better estimate that I will have. But if we do 8 or 16, it's going to take a while. So what we're going to do is we're going to start here on the right endpoint. So area equals. So before we start though, what would our delta x be if we want 4 rectangles? So the way we find it is we say this would be b and this would be a. We say b minus a divided by n. So it would be 2 minus 0 divided by 4. We all know that would be 2 over 4 or 1/2, right? So that's going to be constant every time. The width of every rectangle that we're going to make is going to be 1/2. All right, so we are first going to find f of 2, and then we're going to say that times delta x, 1/2, and so f of 2 is going to be this y value way up here. And so I'm going to draw a rectangle, and the width is going to be 1/2, because from 2 to 1.5 or 3/2, that's 1/2 of a unit on the x-axis. All right, plus, Now I'm going to use the next x value. So that'll be f of 1.5. And then I'm going to say that times 1/2. So if I'm at f of 1.5, that's right here. That's the y value right there, whatever y value that is. That's going to be that rectangle. And then I'm going to say plus, now I'm at 1, so I'm going to say f of 1. That's going to give me the height of my next rectangle. Right here is where f of 1 intersects the graph, right there. All right, and I'm going to draw a rectangle, 1/2 of a unit wide. F of 1 will give me the height of this rectangle, which I think we already know what it is. I'm going to put it there anyway. Then we have to say that times 1/2. And then look at f of 0.5, or look at 0.5. If I go up here, this value right here, that's going to be the height of this last rectangle, whatever that is. So that's f of 0.5 times 1/2. Now, just like with the summation notation, I mean the area, I'm summing all these up. So what I can do, since I'm multiplying by 1/2 every time, is I can say 1/2 times f of 2 plus f of 1.5 plus f of 1 plus f of 0.5. Now the area that we find, you can clearly see that the rectangles are above the curve. So the area that we find is going to be more than the actual area under the curve. All right. Another thing that I want to mention that's very important, I know you may be doing calculations, but listen to this. If I start on the right side, notice that I used f of 2, f of 1.5, f of 1, and f of 0.5. I did not use f of 0. If I would have used f of 0, then I'm creating another rectangle over here somewhere. So if we start on the right endpoint, we're going to use every value on the x until we get to the left endpoint, and we don't use the left endpoint. And it's going to be the same if we start on the left endpoint and go to the right endpoint. We'll start, if we start on the left side, which we'll do next, then we're not going to have f of 2 at the very end. We have to stop so that we have 4 rectangles. Now let's calculate this real fast. All right, so this is going to be 1/2 times f of 2, so it depends on what the function is, and here's our function. That's going to be 5 plus f of 1.5. All right, so I'm going to say 1.5 squared plus 1, and that's 3.25. I was just plugging it in the function, squaring it, and adding 1, plus f of 1 is going to be 2, plus f of 0.5, so 0.5 squared plus 1, that's 1.25. All right. So now let's add all those values up that I have in my brackets. 5 plus 3.25 plus 2 plus 1.25. That's 11.5. Now let's say that times 1/2, or times 0.5. And I got 5.75. So that's 5.75 square units. Now that is called an upper sum because it is actually going to be more than the area under the curve. Or it's going to be more than the actual area under the curve. Again, that's called an upper sum. Or, yeah, I'd call it an upper sum. Because we summed all that up and did that. All right, so now what we're going to do is I'm going to put the exact same curve down. We're going to be able to use some of these calculations, by the way, to help us when we start on the left side. But I'm going to put the exact same curve down, and we're going to start at the left endpoint. And let's see what the left endpoint is going to give us a lower sum, because all the rectangles are going to be below the curve. All right, so our width is going to be the same. Our delta x is still going to be 2 minus 0 divided by 4, because it's got to be the same, because we're doing the same number of rectangles. All right, the difference is we're going to start with the left endpoint. All right, so my area is going to be equal to, so if I start at the left endpoint, that gives me this height right here. And I go over to where my x value is just 1/2 of a unit away, and I stop right there. Okay, so that's f of 0 times 1/2, or 0.5. Now I'm at 0.5, so I'm going to go up here. That's where that would be the height here. And I'm going to go over to my next x value, 1. So that's f of 0.5 times 1/2 plus. Now I'm here at 1. This gives me the height of the graph, or the height of the rectangle. If I do f of 1, see, that's my y value. I'm going to go over to 1.5, because that's 1/2 of a unit away. All right, so that's going to be, that was f of 1 times 1/2 plus, now here at 1.5, or 3/2, it's the same as 3/2. I'm going to go up here to the graph. That's where it would touch, and I'm going to draw my rectangle over 1/2 of a unit. Now notice that makes the fourth rectangle, so I'm not going to do f of 2. All right, my last value is going to be f of 1.5 times 1/2. And so we know we can factor the 1/2 out, and we're going to find f of 0 plus f of 0.5 plus f of 1 plus f of 1.5. All right. Now, we can use some of these values up here. If you remember that this goes with that number, this goes with that number, this goes with that number, and this goes with that number. So we can use those values so we don't have to calculate them again. Now, the only one we don't have is f of 2. So we do need to start out with f of 0. To get that, what was our function? Our function was x squared plus 1, right? It was f of x equals x squared plus 1. And so if I plug in a 0 right there, if I plug in a 0, I'm going to get a 1, right? Plus, and then I have the 0.5 answer here, 1.25. Plus, I have the answer for 1 right here, that was 2. Plus, I have the answer here for 1.5, that was 3.25. And so now I sum up these rectangles. Sum up the area of each one of these rectangles, and I got 7.5. So 7.5, I need to say that times 1/2. And I got 3.75. So that is our lower sum. So by finding the upper sum and lower sum, I know that the actual area is going to be greater than 3.75 and less than 5.75. And that was by just using 4 rectangles. Now, again, it's more work, but the more rectangles we use, and we do have to use like an even number, it needs to be, you wouldn't have to, I guess, but it would be easier to always use an even number since we're going from 0 to 2. For example, and you don't have to copy this down, this is starting on the, this is what it would look like if we let n equals 8. All right, and so we would start, you know, this one is starting on the right endpoint, you can see, because that's the height of the first rectangle. This one is starting on the left endpoint, you can see, because that's the height of the left rectangle. Now what's going to be different here? Though if we have 8, our delta x is going to be 2 minus 0 divided by 8. So really, you know, the width is going to be 1/4. The only thing else that's going to change is that we're going to have to figure out 8 heights, because we have 8 rectangles, and so all the heights of the ones we had before are going to be the same, but the height of 1.75, the height of 1.25, those will all be new. And I'll show you. Here are the answers that you would get if you do that, just to give you an idea. So for the right, starting at the right endpoint, right here, you would get 5.1875. Starting at the left endpoint here, you get 4.1875. So it, you know, our actual area, we know it's between those two. All right. There is some, you know, integrals are going to come into play here. They're just not going to come into play yet. Okay. You have to kind of, you remember you learned the derivative by the limit process, and then you learned an easier way to do derivatives. It's kind of like that. This is the way that people had to do it, you know, back in the Archimedes time. And then once calculus was discovered, there was an easier way that was found. Okay. Now let's go through another one as fast as we can. We don't have a lot of time. There are 4 problems on your homework. Okay. I'm going to work, I guess I'll work one of the harder ones real quick. You may need to use, well, hopefully you won't have to use a graphing utility, but if you don't know what the graph looks like, you may want to go to Desmos. It's a really good, or get the Desmos app for your phone. It's a free graphing utility. You may want to get that just so you can get an idea of what the graph looks like. But I'm sure we all know what the graph of cosine of x looks like. So cosine of x starts at a high point. Actually, it will start at the high point of 1, and then it will cross, and then it will have a low point, and then it will cross, and then it will end at a high point. So the high point, let's say that's -1 there, since I made that two lines. So it's going to cross low point, cross high point. Okay, so it looks something like that. Cosine is equal to 0 here. I'm sorry, 1 here on the x, 0 on the x, 1 on the y. So this is x equals 0, it's y equals 1. This x would be the cosine of pi over 2 is 0. This is 3 pi over 2 because the cosine of 3 pi over 2, no, not 3 pi over 2, I'm sorry, pi. The cosine of pi is -1. The cosine of 3 pi over 2 is 0. And then the cosine of 2 pi is the same as the cosine of 0, it's 1. So we're trying to figure out the area under the curve from x equals 0 to x equals pi over 2 using 4 rectangles. So to find my delta x, I'm going to have to say b minus a. So b is going to be the larger number. So pi over 2 minus, and then the left endpoint was 0, divided by the number of rectangles that we're going to use, so that's 4. Anytime you divide by a whole number, you would want to think about it like it's over 1, and you flip and multiply. So you multiply by 1/4. Dividing by 4, multiplying by 1/4 is the same thing. So my delta x is going to be pi over 8. Okay. Now let's start with the left endpoint of 0, and we know that we're going to have, my width is going to be pi over 8. So the midpoint between 0 and pi over 2 is actually pi over 4. The midpoint between 0 and pi over 4 is pi over 8. And so that's pi over 8 units from 0 to pi over 8. That's pi over 8 units from pi over 8 to pi over 4. If I go another pi over 8 units, I'm at 3 pi over 8. And then if I go another pi over 8 units, I'm at 4 pi over 8, which is pi over 2. So we're going to start with the left endpoint, and we're going to make rectangles starting with the left endpoint. So my first rectangle is going to be f of 0. So it's going to have this height. And then my next rectangle is going to have a height of f of pi over 8. And then my next rectangle is going to have a height of f of pi over 4. And then my last rectangle is going to have a height of 3 pi over 8. So you see, that makes, and my drawing is not the best in the world, but that makes those rectangles. And I believe, actually, if I go here, it's above a little bit. My drawing wasn't very good.
So we start from the left endpoint?
Yeah, we start on the left endpoint first. We could start at either endpoint, but it's actually going to be above, not below, when we make these. All right, so there we go. All right, so we know that the width, and this is going to be with the left endpoint, I'll say sub L. We know the width is going to be pi over 8. And then, since we start at the left endpoint, I'm going to say f of 0 plus f of pi over 8 will give me the height of the next rectangle, plus f of pi over 4 plus f of 3 pi over 8. Now remember, whenever I say f of, that means I have to plug that value in for cosine. So while you may not have trouble finding cosine of 0, you're probably going to have trouble finding cosine of pi over 8. So what you want to do to find the cosine of pi over 8 is you want to make sure that your calculator is in radian mode, and you actually want to put in the value pi over 8 and take the cosine of it. So it has to be in radian mode. So I'm going to go ahead and give you the answer for that because we're running out of time. So whenever you work all of that out and you multiply it times pi over 8, you should get 1.1835 if you round, if you round to 4 decimal places. Now, if I start on the left endpoint, we can actually do it, the right endpoint, we can actually do this without drawing the graph if we know what values we have to use to get our heights. So we know that the width for each rectangle is pi over 8, but instead of starting at 0 to get the height of my first rectangle, I'm going to start at 2 if I do the right endpoint first. Not 2, pi over 2, sorry. I had my other problem stuck in my mind. But I'm here at pi over 2 will give me the height of my first rectangle, plus f of, now go to the next x value, that will be 3 pi over 8, plus, now go to the next x value, that will be f of pi over 4, and then the last x value is going to be f of pi over 8. Now notice that there's 4 values in here. Well, it was n equals 4, so you don't want to have f of 0 in here if you start on the right side. You always leave that last x value out. Now when you work this out, you should get 0.7908. So I do want you to work it out.